Just like we spoke about internal energy, and we said that for a constant composition system, internal energy can be function of pressure, volume, temperature. But if it's constant composition, then it is sufficient to write it as a function of pressure and volume, because the temperature itself can become a function of volume and pressure, right? That's the idea. That's the equation of state. So this reduces to energy, internal energy, as a function of pressure and volume. Or we could write down internal energy as a function of volume and temperature, or we could write it down as a function of temperature and pressure. So we did a lot of work thinking about internal energy as a function of volume and temperature, right? We wrote it down as this way. There is no problem in writing it as a function of pressure and temperature. In fact, that is what we did for the last part of the class. That is how I posted the full derivation. Atkins kind of went into it in a rushed way, as Atkins tends to do every once in a while. I posted the full thing on Slack. Hopefully you went through that. Just one, you can be rigorous about how we got there. So for enthalpy, similarly, we could write down enthalpy as a function of pressure or volume, pressure or temperature, or volume of temperature, volume and temperature. None of these is wrong. Each of these is useful, depends on how you're carrying out your experiment. Since enthalpy tends to correspond, since we have defined the heat capacity at constant pressure, which most rigorously is defined as partial Q divided by partial T at constant pressure, but we don't know how Q changes. That's a path function. And we showed that for any gas at all, this is equal to partial H by partial T at constant pressure, right? This is true for anything. By the way, someone asked about the second problem on the homework. Yeah, that's ideal gas is okay in that one. If you can do it without ideal gas, I would be very impressed. I don't think you can. There is no other way to do it without an ideal gas. So since we have defined this heat capacity, which looks at change in enthalpy with temperature at constant pressure, it becomes natural, not natural. It is kind of nice to think about H as a function of P and T. So let's do that. Let's write it down that way. Later, when we do entropy, you will see this concept of natural variables, which is something very interesting. And you will find that there is actually something special about which variables we use to define a function. It will turn out that we cannot, out of all these three, none of them are actually natural variables. For enthalpy, a natural variable actually involves entropy. We aren't there yet, we will get there. So you can ignore that for now. For now, let's just look at H of PT. So if we have H of PT, what can we say about DH? Any ideas? How do we write down DH? You can speak louder. Partial of partial H, right? With respect to what? P at constant T multiplied by? Correct. And the other one will be partial H by partial T at constant T multiplied by dt. Which of these have we seen before? Second one, what is it? CP is just written above, right? We just saw this. CP is partial H by partial. So, by the way, I hope you're all ready for some multivariable calculus fun. Today, we are going to use something called the triple product rule. It's the day you have all been waiting for. I totally was waiting for it. I got up at 5 a.m. I was so excited about the triple product rule. And then Pakoda gave me angry stares. So why am I up? So we have this. So we can think about change in enthalpy at constant temperature. As a function of pressure and temperature, it will be partial H by partial P, T dP plus Cp dt. We saw a relation like this for du, remember? We had a very, very similar relation. Does anyone remember the relation we had for du? We had, what did we have here? C V dt, right? And what did we have over here? Partial u by pi. Yeah, pi was the name, but what was the partial derivative? It was partial u by partial v at constant T multiplied by dV, right? And this thing was called pi T, the internal pressure. For an ideal gas, this was 0. Do we expect something like this to happen here also for an ideal gas? Let's write down this equation on the next page and let's think about that. So equation 1 says dH is equal to partial H by partial P at constant T dP plus partial H. The second term we already know is Cp dt, right? The question is, can we calculate this for an ideal gas? We can, right? What is H for ideal gas? Well, H is always U plus PV. For ideal gas, H is equal to n degree of freedom multiplied by RT by 2 plus nRT. Does any of this depend on pressure at constant temperature? So what should this be for an ideal gas? 0. For an ideal gas, partial H by partial P at dP is equal to 0. So we get this interesting relation, again, similar to what we had for an ideal gas for internal energy, that dH is equal to Cp dt and du is equal to Cv dt for ideal gas. This is not true in general. For a non-ideal gas, in du, we had the internal pressure multiplied by dV. And for this one, we have this strange partial derivative, partial H by partial P. It's really esoteric, right? How does the enthalpy change with pressure at constant temperature? Who thinks about that? It's really, really strange. Turns out it is important. Turns out it is important enough that Joule and Thomson, who were two very famous scientists, thought about it a lot. And some of the early forms of refrigerators used this coefficient in order to work. So let's think about that. Joule-Thomson effect or Joule-Thomson coefficient. We'll just talk about that, and then we will come back to our equation 1. So in order to get to this coefficient, I'm going to use your favorite relation from multivariable calculus, which is if you're thinking about H as a function of temperature and pressure, and this is really note for you to go and look at those modules, or you're going to suffer in the midterm, I promise. It will be a bit painful. If H is equal to H of Tp, then partial H by partial pressure at constant T is equal to minus partial H by partial temperature at constant T, partial temperature by partial pressure at constant H. Isn't that beautiful? That's the triple product rule for multivariable calculus. So this thing over here is the product of these two things. Once again, have we seen this one? We just saw it. Is Cp, once again, Cp shows up, great. Minus Cp multiplied by partial T by partial P at constant enthalpy. But this one is even stranger. What does it mean to have a constant enthalpy process? Really, really strange, right? So it is this strange looking partial derivative that Joule and Thomson called as Joule-Thomson coefficient. It has the symbol mu. I don't know if Thomson has a P or a not. I think it's without a P. Joule-Thomson. So mu is equal defined, Joule-Thomson coefficient, and I'll tell you why it's important, is defined as partial T by partial P at constant H. Okay, so let's call this one as equation 2, and let's call this as equation 3. So if we use 3 in 2, what do we get? We get partial H by partial T at constant T is equal to minus mu multiplied by Cp, right? And if we take this equation number 4 and put it in equation number 1, then we can see that, no, I messed up something. Right? Partials are funky. partial H by partial P at constant T is equal to minus mu Cp. And if we take this thing and put it over here, what do we get? We get dH. Let me write that down on the next page. Make sure everyone's copied. It's a lot of partial derivative. If anyone came late, you can please come anytime and collect your homework over here. Okay? Just come anytime and collect it. So with this, we get dH is equal to mu minus mu Cp. dH is equal to minus mu Cp dP plus Cp dt. And this is similar. And this is true for any gas, any material, any chemical. Similar to du is equal to pi T dV plus Cv dt. So we just showed earlier that partial H by partial P, partial H by partial P at constant T. We don't need to have dP is equal to 0 for ideal gas, right? So we showed that partial H by partial P at constant T is equal to 0 for ideal gas. What does it say about mu, the Joule-Thomson coefficient for an ideal gas? Why? Cp can be 0, but not for an ideal gas. For an ideal gas, Cp is always, we know what it is. You know, it's non-zero. Yeah, so that's correct. Therefore, so just to write down what you mentioned is, if we look at this relation, equation number 4, equation 4 can be written as partial H by, equation 4 says partial H by partial T, partial P at constant T is equal to minus mu Cp. And we know this is 0 for ideal gas, right? We just showed it earlier. And Cp is not equal to 0 for ideal gas. In fact, how do we know that? Because we know that Cp minus Cv is equal to Nr. And we have calculated both Cv from the number of degrees of freedom, right? It's a constant, it is 3 Nr. So we know Cp is definitely positive, it is never 0. Therefore, mu is equal to 0 for ideal gas. This could be the type of problem you can often get in a, I wouldn't give you a problem such as this, show that the Joule-Thomson coefficient is 0 for an ideal gas in a take-home exam, because you will go to the internet, find the solution, copy it, it's everywhere. But in a closed book exam, this can become a tricky problem. You have to think through all the steps and make sure that you realize what's going on. Any questions about this? So let's call this as equation 5. This is how enthalpy varies as a function of pressure and temperature. So this Joule-Thomson coefficient sounds very strange, you know. Joule-Thomson coefficient, mu, is defined as, what do we define it as? It is partial T by partial P at constant H. This is the definition of Joule-Thomson coefficient. So it sounds strange. Why would you care about such a thing? So it turns out there is something called the Joule-Thomson effect for which it matters. And this Joule-Thomson effect is something used in liquefaction of gases. And I will draw this setup, and Atkins talks about it over 2 pages, nice colorful diagrams. So you can go and look at it, but I will describe to you the basic process. Let's go to the next page. So the Joule-Thomson effect. So this derivative, partial T by partial P at constant H, this is change in temperature by change in pressure for constant enthalpy process. A constant enthalpy process is also known as an isenthalpic process. Okay. So far, what are the ICE process we have seen at? What are the constant processes we have seen at so far? It's a good idea to make a list of those before we get into this. Let's try to remember what are the constant things we have. You have to remind me, all of you. So we just saw isenthalpic. Isenthalpic is what is being held constant. It is H. What else? Isobaric. What is constant there? What else? What is constant there? Okay, I'm going to ask you a question just in a moment. Who said temperature? You said, okay, you be ready. What else? What is constant there? Okay, here's a question for you. For an isothermal process, temperature is constant. Okay, we all agree. What about the internal energy? Is that constant too? Okay, let him answer. I mean, you want it.
Yeah, he said it.
Huh? Isothermal is dT is equal to 0. I'm asking what happens to the internal energy in an isothermal process? Will internal energy also be constant? What can we say about du in general? dq plus dw, that's correct, but think of u as a function of volume and temperature. Pi t dv plus cv dt. So isothermal process is d2 is equal to 0. Does it always mean that du is also going to be 0? Only for an ideal gas. And the reason I bring this up is because I have taught this class, I don't know, 3 times now maybe. There have been times where 50% of the class makes this mistake. Isothermal is not constant internal energy. Constant temperature is not constant internal energy. Constant temperature is constant internal energy only for an ideal gas. If you don't have an ideal gas, which is pretty much anything in the world, then pi t is non-zero. Okay? And just because we have a constant temperature process does not mean the volume is also not changing, right? So it's really important to remember here that isothermal is not the same as iso-internal energy. These relations that we wrote down where du is equal to Cp dt, Cv dt is true only for an ideal gas. So this is not true in general. Only for an ideal gas it is true. So these are the 4 we have seen so far. And later we will be looking at adiabatic process and isoentropic process and things like that. But these 4 we have. Did we miss any iso? There's also ISO knowledge process when you take class over a semester and you don't learn anything at the end of it. It's a negative knowledge process. You feel like you learned less. You actually, it has happened to me one time. It's terrible during grad school. So let's talk about this Joule-Thomson coefficient effect now, which is a way to implement an isenthalpic process. So now this isobaric process is very easy to imagine, right? If you have a chemical reaction going on here exposed to the atmosphere, that's an isobaric process, right? If you have a chemical reaction going on in this, that's an isochoric process. Isothermal, well, if you have it well insulated, then it's probably an isothermal process, right? The temperature, you can implement isothermal by keeping the, not insulated, if you keep it in contact with a heat bath, which forces the temperature to be constant. Does anyone know example of isenthalpic process in nature? It actually happens in volcanoes quite a lot. Well, volcanoes are forming. So in nature, there are examples when isenthalpic processes happen. So my wife is a geologist and she seems to be very interested in them. I think they're very strange because it's hard to think about them in a natural setting. These 3 are more natural. So let's see what happens in Joule-Thomson. So Joule-Thomson effect is you have a big apparatus. This apparatus is thermally insulated. thermally insulated does not mean temperature is same. Thermally insulated means heat cannot go in or out. Okay, so delta Q is equal to 0. And this apparatus is fixed in shape and size. It cannot change its volume, which means delta W is equal to 0. And everything inside this is our system, right? So it's thermally insulated, it's fixed in shape and size. And so what Joule-Thomson does is that inside this, it has a device which has a very narrow entrance. And through this narrow entrance, you pass in gas at high pressure. Okay? You pass in gas through a very, very narrow pore at high pressure. And at this other end, you have a much bigger exit pathway for the gas. So what will happen to the pressure of the gas as it goes out through a bigger, broader pathway? What will happen? What will decrease? How do you know? There is a name for that principle in physics. Huh? Bernoulli's principle. Does it not apply to this? We don't have to worry about it. If you have forgotten Bernoulli's principle, that's okay. But you're right. This gas becomes at low pressure. And one of the simplest way to think about it is think of an ideal gas at least, right? PV is equal to nRT. But that's where it becomes dodgy. When you say, oh, I'm going to use PV is equal to nRT to explain that volume increasing means pressure goes down, you're assuming something. You're assuming that the temperature stays same. That's not true. But in this case, it is designed in such a way, and if you really want to prove that the pressure goes down, you have to invoke Bernoulli's principle or it won't happen. So by the way, this is done in Atkins in 2.D.2. And again, if you don't find in your book, just send me a message and I will put it on Slack. It is in one of those sections called How is it done? Or something like that. A strange name. No, how that is done. The same thing. How that is done. So it is not obvious from this as to why should the enthalpy be constant, right? For this process, why should this be a constant enthalpy process? This is not obvious. So in order to think about that, we can think about H plus U plus PV. And I will give you an intuitive proof of why is enthalpy constant in this. If you really want to see why is enthalpy constant, please go and read 2.D.2, and that goes through it very systematically. But imagine H is equal to U plus PV. And now imagine that this term dominates, okay? The pressure is so high that the contribution of internal energy to the enthalpy is very tiny. I'm not saying this is always true, but let's imagine here that is true, that the pressure is so very high that this is approximately PV, let's say. Now, in over here, when you passed the gas in, what did you have? You had P high multiplied by V low, right? Very high pressure multiplied by very low volume. On the right side, what do you have? You have P low because the pressure goes down. You have just opened up a big thing for it to get out of, multiplied by very, very high volume. So you can kind of see that why PV is approximately constant. So you can kind of see why if PV is what dominates in the enthalpy, then maybe it is a constant enthalpy process. But if you really want to think about why is it a constant enthalpy process, you should read this section in Atkins. I'm not going to be drilling you on it, but you have to take my word for now that this construction where you pass gas through a high pressure, through a tiny pore, and then let it get out at low pressure through a big pore is a constant enthalpy process. But the question I do want us to think about very, very carefully today is what happens to the temperature of the gas. So we agreed kind of intuitively that the pressure goes down, but can anyone reason with me what happens to the temperature? Will the gas keep the same temperature? Will it heat up or will it cool down? If it was an ideal gas, then maybe it will stay the same, right? Especially for this argument. If PV is equal to constant, that means temperature is going to be constant. So what we are trying to think about here, and that's where you can directly see why the Joule-Thomson coefficient matters. We are I am asking you that what is going to be the change in temperature with respect to the change in pressure for this process that goes on at constant enthalpy. We know that this is 0 for ideal gas. We just saw that. The question is, what will it be for this process? And you don't have to give to me a mathematical argument. You can give to me an intuitive argument. Any ideas?
So let's just save so much less pressure. Not going to be bumping into each other much. So, gas will dissipate, therefore temperature should decrease.
Temperature should decrease. You are absolutely, not absolutely correct, but you are absolutely in the right direction. Okay, good job. Close enough. You can go to bed happy today. Or any other day, I don't stop you. So what's your name? Daniel. So what Daniel, who sits next to Marco, said is Daniel wants me to think about the potential energy curve, okay, of how atoms talk to each other. If it's an ideal gas, the potential energy curve is boring, right? It's just nothing. But for a real gas, we know potential energy curve looks something like this. So when let me draw the contraption once again here. You had gas going through a very narrow pore, and then gas coming out of a very big exit. So in this case, when the gas is going through a very tiny pore, which one will have, where will the gas have higher value of interparticle separation? In the beginning or while going out? While going out, right? There is so much space that everything is going far from each other. So in the beginning, if you were somewhere here, or wherever you were here, maybe you were here, maybe you were here, maybe you were here. So this is during the entry of the gas. Okay, and here my U is my potential energy. Actually, let's not call it U because we use U for internal energy. So that's going to be total confusing. Let's just call it potential energy. So potential energy of the gas during entry is here. And when it goes and expands, the average particle separation increases. So which way should I move on this curve, to the left or to the right? To the right, right? Because the average interparticle separation has increased. So this thing should move over here. So what has happened to my potential energy during this process? It has gone up. Now remember, this whole setup was delta Q is equal to 0 and delta W is equal to 0. So what can we say about the total internal energy change of the process? 0. First law of thermodynamics, you cannot change it. Einstein said, that quantum mechanics might become wrong one day, relativity might become wrong one day, thermodynamics is going to stay. So the first law of thermodynamics, we cannot fight. So we know delta U is equal to 0. And what does delta U come from? Delta U is change in kinetic energy plus change in potential energy. And we know this is 0. And we know potential energy is positive, right? This term is positive. The potential energy increased as the particle separation increased. So what can we say about the kinetic energy then? It has to be negative. The kinetic energy must go down. This must be negative, because if this was also positive, then negative and positive plus positive cannot be 0, right? So kinetic energy went down. And we know that kinetic energy is proportional to temperature, right? Therefore, temperature also went down. This is what Daniel expressed very precisely by nodding his head and in 5 words. And I just went through the details. He's very smart. Right? This is what you had thought. Yeah. You have the same idea. That's what he said. Yeah. You had it all laid out in your head. I know. Is this clear? And this wouldn't have happened for an ideal gas. For an ideal gas, this curve over here would have looked something like this, right? potential energy versus R for an ideal gas. If you are here, if you separate it out to a further distance, potential energy still stays at zero. You can also say physically for this, if the potential energy stays zero, and we know change in internal energy is zero, then the change in kinetic energy also must be zero. So for ideal gas, delta potential energy is equal to zero. Therefore, delta kinetic energy is equal to zero. So this shows as to why. So what does this tell us about? Okay, final thing. So what does this tell about the Joule-Thomson coefficient then? For a non-ideal gas, is the Joule-Thomson coefficient positive or negative? You have to look at this derivative up top. What happened to delta P? Was delta P positive or negative? Who said positive? Think about it. Pressure went down or up? So this can be confusing because what are we talking about? Are we talking about delta P as P final minus P initial, or P initial minus P final, right? So P initial is more than P final, and P initial is also more than P final, right? The kinetic energy went down. So therefore, delta P, if you define it as P initial minus P final, then delta P is positive. So, and delta T is also positive. So what does this mean about mu? Positive. So for any material, the Joule-Thomson coefficient is positive. Only for a perfect gas, it is equal to zero. And people try to use this to define, to come up with refrigerators. I don't think it was very popular. I don't think existing refrigerators use this technology, even though you might think that maybe there is some compression going on. Maybe this is what's happening, but this is really not what is happening. You can go and read up on Joule-Thomson refrigerators. They tried to design a fridge based on this principle. It was not very successful. But this gives us, why did we do this? Why did we do this? Well, it's fun, right? I do this because it's fun. And essentially all of this, what we are doing is to come up with so just like last page, we wrote down all the iso processes that we have thought of, right? We had isenthalpic, isobaric, isothermal, isochoric. Let's also make a list now about all the state functions that we have looked at. What are the state functions we have considered so far? Which is the first one? There is a lot of murmuring going on. Did I write something wrong? Yeah, depends on how you define delta, right? If delta is final minus initial, then it is negative. But the point being that either both are positive or both are negative. So that's right. So whoever said it's positive, it's actually correct. Depends on how you define it. But the point being that both have the same sign. Sorry, this can be confusing. So what are the state functions we have considered so far? Internal energy, everyone's favorite. What else? Huh? Enthalpy H. And H is related to U as U plus PV. Typically, pressure and volume can also be thought of as state function. There is nothing wrong in it, but most of the times we tend to think of these as state variables. There is really nothing wrong in calling them state functions. They are also state functions. We can manipulate things around. And we wrote down relations for how these state functions vary as a function of control parameters, right? So once again, this relation I have written so many times today because it is just so important. du is equal to pi t dv plus cv dt is always true. dh is equal to minus mu Joule-Thomson coefficient Cp dp plus Cp dt is always true. And these relations are important because U and H are really how we can look into a material, right? And a microscope is one way to look inside a molecule or a material, right? You make a fancy electron microscope and you can see directly what's going on. But that's not the only way. U and H carry information about what makes up a given chemical, what is the nature of bonding inside that chemical. So if you carry out a process, depending on whether you are doing it at constant volume, constant temperature, or maybe you are changing both the parameters, you can look up books for value of the heat capacity, for value of the internal pressure, and you can go and say something about the internal energy. You can go and say something about the enthalpy. So these are very powerful tools which are used everywhere, from material science to chemistry to biochemistry to biophysics. These type of relations are how people were able to understand what makes a DNA molecule stable, what makes RNA stable, what makes a protein stable. You know, hydrophobic forces will have different types of U than hydrophilic forces. And this is our way to study all that. And that's why we always end up manipulating these partial derivatives. So I want to start the next topic, but I won't do it right now. I will start on Friday, which is adiabatic change, which is when you do a change, keeping Q is equal to delta Q is equal to 0. You don't give any heat to a system. So in this example, in the Joule-Thomson, we saw there was no heat going inside the system, but work was also 0. So an adiabatic change or an adiabatic process is where delta Q is equal to 0, but delta W does not have to be 0. It could be 0, but it doesn't have to be. The definition of an adiabatic change is when delta Q is equal to 0. We will look at adiabatic change and we will try to study how the temperature, pressure, and volume vary during an adiabatic change. So you can read this up in Atkins. The ratio of Cp by Cv will matter a lot over here. This is where the degrees of freedom starts to matter a little bit. And if you haven't taken your homework, you can take it over here, and I will see you Friday.